Thanks, Marissa. For those on the call that don't know me, I am Charlene Sylvester. I am with the Coastal Hydraulics Lab, Coastal Engineering branch. I actually sit down at the Joint Airborne LiDAR Bathymetry Technical Center of Expertise in Kiln, Mississippi, along with my colleague Scott Spurgeon. And today we are going to share some progress that we're making on this work unit that is developing a next generation framework for calculating coastal volume change. This is a work unit that I am proud to sort of co-PI alongside my colleague Scott Spurgeon at Jobeltex, as well as Sam Jackson from the um, the environmental lab. So I'll be starting off with just an introduction to our team members whose faces are all, on the slide here. So in the talk today, we have actually a lot to share. So we did want to request that any questions or conversation be held for the end so we can get through the material and hopefully have some really good discussion. But I'm going to be just providing a short overview of the project itself, what our motivation is, and our planned research roadmap. Scott is going to detail some work that he has led in terms of compiling a literature review for the projects, as well as a workflow that he has, technical workflow that he has been working on for looking at space-time cubes, which he'll elaborate on. Shane Nichols O'Neill is our ORISE fellow that we were happy and privileged to welcome to the team last year. So he is supporting some preliminary work that we are doing, assessing bias that might be present in volume quantities. Brooke Walker is a new physical scientist on our research team that has been supporting some of the volume calculations work in direct support of Shane, as well as one of our other tasks. Sam Jackson with the Environmental Lab, he is a research forester that is helping us to begin to integrate some of advanced land cover and dune vegetation metrics into the volumes and see what that might start to look like. And then finally, Loderai, we had literally just welcomed to our team maybe 2 weeks ago, if memory is serving me correct. She is a contract support under the Taylor Woolperk contract, and she will be supporting some of the volume partitioning work that is only really just getting off the ground now that we have her wonderful support. And I should also say that we have a fairly nice well-rounded PDT membership with scientists and engineers from the Coastal Hydraulics Labs, and then 4 different districts, being Mobile, Philadelphia, Jacksonville, and New York. But I would say that this project is welcoming additional PDT participation at any point on our roadmap, and we would be grateful for your participation and your feedback. And at the end, we have a means by which you can provide feedback if you don't feel like emailing any one of us individual. And so kind of the topics that you sort of see listed there are what each individual team member will be speaking towards today. So to start off with a project background and motivation, this work unit was really born out of the 2003 Statement of Need process, where we identified with some of our district partners a need for some tactical R&D aimed at advancing spatiotemporal sediment volume change analysis tools to promote efficiencies in the sediment budget development and maintenance process. The current spatial framework that we would typically use for calculating volume quantities is provided on the right-hand side of the slide, utilizing an existing framework that's based off of DEMs of difference, say between 2 survey data sets, and then we compile or calculate those volumes in a series of, in general, alongshore volume change bins that have a given width along the coast. And then some of the quantities or products that come out of that existing framework include those DEMs of difference, or what we call difference rasters, a series of shoreline vectors, and then the different volume quantities, whether that's a total or a net volume change within that volume change bin. There's also a volume that we compute that lies above sort of a mean high water reference. That's a NAVD 88 reference. and then some shoreline change metrics, as well as different statistics on the volume change as well. So all of that information tends to be really super useful for engineers and scientists to look at. But really, it's just a snapshot in time, right? It's a volume change from time 1 to time 2, and I'm jumping ahead. But what we see as one of the primary limitations of this kind of framework is that these volume change bins that we're calculating volumes on are fixed in space. So here we have zoomed in to an area on Dauphin Island. You're kind of seeing those beach volume change quantities in cubic yards. So this would have been a post-Sally analysis. So a 2020 data set compared to, I want to say the 2016 was sort of the pre-storm data set used in this example. And those are those colored bins in yellows and pinks and greens. And then, of course, that difference raster product is underlaid, and we can see where the volume change bins sort of fall short of the full barrier island. And there's a lot of reasons why it would be good to do that. So for example, in an area with significant coastal infrastructure, normally these volume change bins are defined with a baseline that we define along the first line of infrastructure. So that might be like a coastal road or a row of, beachfront homes. And really the purpose of that is to define the extent over which we calculate volumes. And that does allow you to sort of exclude areas of the data coverage that might have some artifacts related to vegetation and or the bare earth removal process in the DEM compilation. So that really you're calculating like a true, beach volume. But that being said, as we do volume change analysis sort of through, say, all time, we see it becomes necessary to change these volume change bins so that we're capturing sort of the results of, physical processes that are responsible for the change in the beach. And so in order to capture, things like barrier island rollover and or even overwash, from a storm, it might become necessary as we go through time to modify these volume change bins. So for one, that tends to be a somewhat labor-intensive process. It can also be subjective depending on the technician that is sort of defining those volume change bins. And then finally, it makes it really difficult to compare the volumes through time, that sort of temporal record of volumes, because sort of the bin size or the area in which we're calculating, say, a volume quantity is not the same through time. And so that can kind of limit developing that broader, understanding of coastal change, which includes not just, a general sense of maybe where sediment is going within the system, but sort of the transport direction of that sediment is something we would like to be able to capture. And so we received a new start under the Coastal Inlets Research Program in FY24. We received funding late in the FY due to delayed appropriations. We really didn't start until April of 2024, but we are addressing that requirement for a flexible volume change framework. And to do that, we are leveraging work that's going underway in other CIRP, research programs, whether they be for geomorphic feature extraction or morphometric mapping. That's that classification, R&D, together with multi-temporal space-time sort of analysis and some conformal mapping approaches that Dr. Justin Schaller and Dr. Katie McFerrin have been developing under their CIRP Inlets project. And again, we want to improve both the characterization and quantification of these volumes for coastal projects in support of that sediment budget development process, but also for operations and maintenance and project monitoring. So of course, we're currently in year 2 this FY, and then I know there's a lot of uncertainty, for next year. We hope to be able to continue this work into next year as well. And so this is our project, our busy project roadmap. shown here. The items in green that you see in FY24 have largely, been completed. As I had mentioned, we welcomed aboard our ORISE fellow Shane, who will speak a little bit later. We've conducted an extensive data compilation for data sets that are areas of interest that have been identified by our PDT members. So Scott will touch upon that very quickly. And then we've done a lot of tech transfer and sharing of knowledge and technical expertise just among the members on our team. So we have sort of the full gamut of like junior researcher all the way to sort of, senior researcher. So we've really just been trying to increase everybody's kind of awareness and knowledge of sort of the current state of the art and conducting and performing volume change compilations. And then we did start that literature review that Scott will also talk about. And this year in FY25, we are wrapping up that literature review, and we've begun to work on the other items that you see there in FY25 that are shown in yellow. So that being that sort of spatio-temporal time cube-based analysis, and there it's just listed as hotspot analysis. We're doing some preliminary work on bias assessments that Shane will talk about. And again, I mentioned we're really just getting started on the volume partitioning portion of things. And then this talk today, I think technically counts as a tech transfer activity. So we're happy to say that we're doing that as well. But we do have a larger full PDT meeting, I think, scheduled for maybe the August timeframe. I'd have to double check on that date. But if you're interested in participating in that meeting, you would be welcome there as well. And then the following year, FY26, of course, pending funding, we'd be working on doing any needed refinements to these methods and getting some products into the hands of engineers who could potentially use them. We also want to apply the methods to additional pilot sites and then formalize any products that would come out of this work unit. And so with that, I will hand it over to Scott, who is going to tell you about the work that he's been supporting for this project. Thank you.
Thanks, Charlene. Good afternoon, everybody. My name is Scott Spurgeon. I'm a research civil engineer at the Army Corps of Engineers Coastal Hydraulics Laboratory. I do sit with Charlene down at the Jobaltech's office in Kiln, Mississippi. Today, I'll really cover the literature review that is wrapping up, and then I'll get into kind of some of the preliminary space-time cube work that I've also been working on. So getting into the literature review on the next slide, this was really the start of our project, and it was really aimed at determining the state of the art related to multi-temporal change detection in the coastal environment. We're wanting to make sure that we're identifying any sort of data requirements for change analysis, identifying existing tools, and kind of looking at how is change detection currently being done, what's the state of the art practices, what are the best practices, and then also considering things like errors and uncertainties. And so you can see our list of topics there that include kind of the simple to more complex approaches, such as the simple approach of using shoreline change as kind of a proxy for volume change, all the way up to the more complex approaches of DEM of difference methodology or a space-time cube methodology. And then, like I said, we also covered a number of errors and uncertainties, and a great discussion on that Charlene headed up. And so it really is a full literature review. We tried to be as robust as possible, but it is really focused on the morphology change detection. We're not necessarily talking as much about the environmental factors such as vegetation or anthropogenic change detection. But we did pull more than 75 pieces of literature into a tracking spreadsheet. We actually, I think I looked at it today, and I think we have close to 100 pieces of literature now, and over 75 of those we actually used for the literature review. And this spreadsheet really tries to cover every important field that you might want in a literature review, things like not only the title and authors, but also the abstract, any summary and key points, any quotes that were particularly important, and then other categories and other things to kind of filter the literature so you can kind of get an idea of where we're pulling from. And then I also have, we also included kind of a current status, whether we actually used it in the literature review or whether we reviewed that literature and decided against using it in the literature review because it wasn't as pertinent. But we included all of the literature that we pulled down. So like I said, it was close to 100 different pieces of literature and references. And so that is kind of morphed itself into its own deliverable alongside literature review, just so that people can kind of see the full breadth of analysis that we did and the look into literature review. So you can scan that QR code and get to that tracking document and just kind of see all the different literature we looked at. We looked at publications from, I think, as early as 1976 to 2024, and we pulled a number of those for our review. So that review is in review right now. It is a special report, and it's in review. So we're definitely excited about that coming out this FY, hopefully. And so getting into the space-time cube side of things, our pilot area for the space-time cube analysis is the Mississippi and Alabama Barrier Islands. These islands are part of the Mississippi Coastal Improvements Project, or MISSIP, and this area really aligns well with other ongoing work in the area, such as a sediment budget update that's reimbursable, as well as existing volume change products, advanced land cover and vegetation metrics. There's a lot of data here, and there's a lot of work that's already been done and that is going on currently. So we definitely felt like this was a great area to do some analysis with. And so for the space-time cube analysis in particular, our data requirements are pretty specific in that we were really looking at high resolution digital elevation models, either 3 meter or ideally 1 meter resolution, just so that we could really look at those individual features instead of using a 10 meter raster or something coarser, where you wouldn't be able to resolve individual features. At a 1 meter resolution, we're able to resolve individual dunes or individual portions of the beach. And so part of the space-time cube analysis really requires data sets across a temporal span that you have to have at least 10 temporally unique time periods for the statistics to work properly. And so as you can see there in the bottom right figure, a lot of these islands have more than 10, have closer to 14 or 15 different data sets that are available. And most of those are National Coastal Mapping Program or NCMP products, which are high resolution products that really fit that high spatial resolution, and they're topobathymetric products as well. So we're able to not just do analysis on the topography, but we're able to do some analysis on the bathymetry as well, which is really, really ideal for this case. And so in addition to all of those kind of spatial resolution and temporal resolution and how many data sets we have, we also wanted to make sure that we had adequate geospatial metadata for each of those data sets, just to make sure that we're in consistent datum transformations and we're doing everything according to the same units and everything else. So that way, when we're comparing different data sets, we're really comparing apples to apples. So that gets our kind of pilot area out of the way, but I've been talking about space-time cubes and haven't really introduced those. So space-time cubes really are a geostatistical tool, and the emphasis there really is on the statistical side. Like I said, these require 10 different time slices, and so that different statistics can be run on them. Typically, the first two dimensions in this space-time cube are the X and Y, which is just your typical plane in your geospatial realm. And then the third dimension is typically time, and you still have X and Y, and each of those XY points has a elevation. But that third dimension in the space-time cube specifically is time. And so we talk about time slices, where each plane and each elevation from a different time period is a slice, and then each one has its own X, Y, and elevation within that time slice. And so space-time cubes provide statistical analysis methods across the entire domain. We can do things like hotspot trend analysis, spatial pattern identification, time series forecasting, a lot of really, really great tools that ArcGIS Pro provides. And that's really in that geospatial framework. And so that allows for really, really great visuals and analysis to be done, all within their own tool sets that they provide. So I've been working on a workflow to really look at how we can go about this, because there's a decent amount of preparation and steps that have to be taken before you even get to the space-time cube. And that includes things like doing all of your data sourcing and preparation, making sure everything is in the same datum and same projections, and then getting all of your different data sets into a mosaic data set architecture, which allows you to stack data sets, and then specify when those data sets were collected so that ArcGIS Pro understands when each was collected, and is able to stack them temporally and understand that kind of temporal Z, Z layer, or that third dimension in the space-time cube. And so once you make the mosaic dataset multidimensional and move over to a cloud raster format, we then can create a space-time cube. And then from there, we can do different sets of analysis, different sets of visualization. The visualization is both in 2D and 3D, and the two different visualizations are actually providing you a little bit different information. So the bottom two figures here are examples from some emerging hotspot analysis, where the left figure there is a 2D and the right figure is a 3D, and they do provide different data. For this in particular, I wanted to note that we typically, as coastal engineers, think about hotspot analysis as erosional hotspot analysis, to where your hotspots are your erosional hotspots. But in this case, this is really just looking at the values within the rasters and telling you where there's a hotspot. So for our particular case, a hotspot is actually going to represent just a high elevation compared to the neighbors that it surrounds. And so as you can see there on the right figure, where we have the 3D visualization, you can see kind of where you would expect to have dunes around that island. You have those hotspots, and then the rest of the island is kind of neither a hotspot or a cold spot. And then most of your bathymetry is considered a cold spot because it's low elevation. So we're not necessarily talking about erosional hotspots or erosional cold spots at this stage, but we're talking about the overall elevations and what they how they compare to their neighbors. However, on the left side there, we have the 2D visualization, and that is really the trend analysis. So it's able to tell us, based on statistical analysis, if there's a new hotspot or an emerging high elevation, or if there's an emerging low elevation. So we're able to kind of see some of the trends that is happening with those elevations. So that's getting us closer to what we might typically think about when we think about erosional hotspots or cold spots, but this is really talking about trends in particular. So there's a lot of great products that are available here. This is just one of them when we're talking about hotspot analysis, but there's a lot more. So getting into some of the best practices, these best practices are really going to be covered in a technical note that is going to be submitted later this year and hopefully published next year, but I'll just quickly kind of go over the highlights. First and foremost, the finest possible resolution of the space-time cube really is governed by the smallest cell size represented by your data sets. You don't want to make a space-time cube at 1 meter when all of your input data sets are at 10 meters, because you're really going to be interpolating and you're going to get a lot of interpolation artifacts. So that's why we really focused on getting high resolution data to begin with, so we could have high resolution space-time cubes. In addition to that, the file formats for mosaic datasets can be a little bit finicky in ArcPro. We typically found that GeoTIFFs or NetCDF files worked better than others, and so we just suggested that. Third, kind of I think the most important lesson learned from this analysis is we found that we had somewhat consistent errors with actually creating that space-time cube, one of those final steps from the multi-dimensional raster layer, and this often occurred whenever we were trying to create a space-time cube with a lot of bins in it, or a lot of X, Y, Z points. And this was really twofold. One was, oftentimes I would go to create a space-time cube that just had more than the 2 billion bin limit, which is just a hard limit that we found is just limited by the tool itself. It just won't create it. And then other times, even if I was under that 2 billion bin limit, we'd sometimes get raster to NumPy array errors or other Python-based errors that, while we were under that maximum limit, it just still overwhelmed the tools because we just had too many bins. And so we're able to kind of reduce that by either reducing the overall extent that we're looking at, or by reducing the resolution, so that way we don't have as many bins for that same amount of space. And then the fourth point here is that we can also reduce the amount of data sets that we have, or the amount of temporal time steps that we have, even if you don't have to reduce the data steps that much, just because if data isn't really collected at regular intervals, which most of the time LiDAR isn't super regular, the time step interval for the space-time cube is going to be the smallest time gap between data sets. So if you have a span of 10 years and your smallest time gap between two data sets is 6 months, it's going to create 6 month time spaces for every single temporal bin, and so that may mean that some of your slices are just empty data, and so it's still going to count against your bin limit even though you're not really contributing data, and that's more of an interpolated data. So we found sometimes it's worth taking out a data set or two just to increase that temporal bin size closer to something like a year or 2 years, especially if you're going across the span of 10 or 20 years. You don't need 6-month time intervals just to create that many bins. So like I said, this is kind of getting into the weeds, but there will be a lot more weeds to get into in the technical note, which is kind of our next steps. That technical note is really going to go into a lot of that, a lot of those best practices and what we found with these tools. Like we talked about, kind of the best practices with kind of the soft cap of number of bins of what kind of overwhelms the Python versus what the absolute cap is on number of bins. And in addition to that, we're also going to start next year into looking into actual products and analysis, looking at what that emerging hotspot analysis can do for us, what other tools within the space-time pattern toolbox and the time series forecasting toolbox can do, and then just looking at other products, other analysis that we might be able to do with those space-time cubes. There's a wealth of tools that Esri provides and others provide, and so we definitely want to look at alternative testing tools outside of Esri, looking at file formats other than NetCDF or CRF to see if those resolve some of the errors with bins, and just kind of looking at all the different options that we have here. So this is in early draft right now, this workflow, but we're definitely excited to get it out. So I'll hand it over to Shane to talk about assessment of bias and DEMs of difference.
Thanks, Scott. Can you guys hear me okay? Okay, great. So my name is Shane Nichols O'Neill. I'm an ORISE fellow, so I joined the team a couple months ago. So far, my work on the team has been focused on elevation bias. So if you can just go to their slide for me, thank you very much. So what is elevation bias? Well, these products that are being input to things like the spacetime cube that Scott's working on, or various other change-based analysis like change detection, volume estimates, habitat suitability, they're all dependent on the inputs. And so in the case of elevation, sometimes there's some error involved. Maybe it's the LiDAR sensor itself and details related to that. The surface related, the difference between analyzing deeper water versus shallower water, or maybe it's processing where you're converting from LiDAR points to a DEM. Maybe you're having problems, removing structures to go to your bare earth DEM. There's a bunch of different things that can, cause a small error in the elevation that can potentially add up as you're looking over larger areas. So the goal is to be able to identify and then filter some of this elevation bias just to improve the products to be as good as possible. We have some elevation data for this project that's going back 20 years, and so some of the technology has improved, and we're just trying to keep everything, at that same level. And so here, there's a figure, an example at Cat Island from a 2016 NCMP data set where we see some banding in the bathymetry. So these are kind of like one example of what we're looking at, trying to account for this and then, provide some solutions. How do we identify it in general instead of visually inspecting all of your data? One of the first steps is we're making these elevation difference versus elevation plots for different islands at different time. For example, this first one we see here is from Dolphin Island. And so the shape of the plot can tell you, what is going on during that time period. For example, is it a physical process? Is it some type of human intervention? Or maybe it's related to, processing or data error, where this Dolphin Island figure, there's three distinct shapes. You have that downward trend at the bathymetry from about -2 to 0 meters. That's just related to the two data sets that we're using, where one has bathymetry, one does not. Towards the lower elevations, like 0 to 4, you see significant change. That makes sense as it's closer to the water. And then as you go to higher elevations, there's limited change. So that kind of tells you, okay, there's limited bias. This data set looks pretty good. You can look into further details, but in terms of elevation bias, this one's solid. Now, if we take a look at this Cat Island plot from 2016 to 2019, For topography, we kind of see a similar situation where at higher elevation, there's limited change. Between 0 to 2 meters, we have both positive and negative change. But the thing that's interesting here is that shape in the bathymetry from -3 to 0, where it's sporadic. There's not like a definite trend going on. And so this kind of sporadic shape, or this lack of structure, kind of tells us, okay, maybe there's something going on in the data. Let's take a closer look. And so what are some potential causes that we specifically see in our data? Well, like I mentioned before, GPS technology has improved drastically over the period of time that we're looking at data, and so maybe that is part of it. And then different types of calibration for bathymetry analysis with LiDAR. Do we see changes based on what depth and what kind of condition you're looking at? So those are the types of things we're looking at and trying to solve. So if you just go to the next slide for me. This is like a specific example of like trying to find a solution or to provide a filter to improve the data that we were looking at before from Cat Island. That banding we see is related to the LiDAR flight lines. And so we can go in and do some type of zonal correction where, for each flight line, we can do some analysis based on the 2019 data set and use that as a reference to be able to tell, okay, what is the general error in these different locations? So we're trying to have a solution for this like spatially distributed error. So once we can point out that error or that bias, we can go in and alter it as needed, and then have an improved data set. And so the actual volume change calculations are currently in progress, and my colleague Brooke is going to look at that in a second. But for moving forward, we're looking to identify different types of bias beyond this example here, and then look for different techniques that can improve our data sets and just ensure they're in their best state going into these different change detection analyses. So I'm going to hand it off to Brooke.
Thanks, Shane. So my name is Brooke Walker. I am going to talk about the volume change and how we're setting the stage for a flexible framework. If you could go ahead and go to the next slide. Thanks, Charlene. So to begin setting the stage for a flexible volume change framework, we're conducting a detailed volume change analysis using a couple of different pieces of JobbleText technology that has existed in various iterations. Data set coverage for this analysis covers the larger midship area of interest from Cat Island to Ship Island, but we include Dolphin Island as well because it's the only Mississippi-Alabama barrier island that has significant infrastructure and a history of engineering interventions. The Dolphin Island panels, as I have in this slide, and I have in the next 3 slides, or in the next 2 slides after this one, you'll see the actually it's going to be the after elevation, the before elevation, and then it's going to be the difference raster between the two, the elevation difference. And so this one shows the 2018 to 2020 volume change. I want to note that purple is deposition and orange is erosion. And this slide also covers what the data sets that I'm going to cover, or that I'm looking at specifically for this initial volume change analysis. If you could go to the next slide, please, Charlene. Okay, so the JobbleText Quick Response Toolbox is a big part of this flexible framework that we're developing. We are using some existing 2020 post-SALI volume change bins, which allows us to start at the step 4, volume by zonal statistics within the toolbox. And we're using these existing volume change bins to save time because it doesn't require the manual digitization of a baseline or transect generation and reduces the duplication of effort. Additionally, it enables the quantification of volumes in a series of shore perpendicular bins, and it'll be easy for us to compare the volumes produced by the companion multi-dataset toolbox. The analysis evaluates the sensitivity of bin size on volume quantities, and will further define the define the requirements for the flexible framework as we look further into adjusting for bias, and we expand the analysis to the rest of the Mississippi area of interest, Mississippi Barrier Island area of interest. And so on this side, we have the 2016 to 2018 volume change for Dauphin Island. And something I want to note is that if you look at our distribution at this very bottom image, we have a pretty significant mean difference of negative 0.23 meters. And so I'm going to be working with Shane to figure out where that potential bias is coming from and how much that bias is contributing to our calculated volumes. So I'm looking forward to working with Shane on that. Could you go to the next slide, please, Shane? Thank you. So I've been saying difference or elevation difference a good bit, and I just want to take a minute to define that. So elevation difference is defined as the difference between DEMs from two time periods, before and after. For example, before and after a storm event, like the 2020 and the 2018 from my first slide, or about a decadal period, which is what I'll eventually be looking at when I compare the 2018 to the 2011 elevation. So we're looking at a cell-by-cell comparison of before and after elevation using Z difference equals Z after minus Z before, where Z difference is the change in elevation for elevation surveyed later, Z after, and earlier Z before. And Charlene was helpful for me to provide a reference there for those equations and for additional information about those, how we calculate volume change. And then before we move to the next slide, I also want to highlight how we segmented the Dauphin Island for this analysis. So we have segment 1, which is the bends along the Gulf side of Dauphin Island. Segment 2 bends are along the Mississippi Sound, and segment 3 bends are along Little Dauphin Island, which is that little upward or northwest leg of Dauphin Island, the one that points to the northwest. And we segmented them to show or to enable a more granular data analysis so we could dive a little deeper into how those different sections of the island were behaving. So there are many ways to visualize volume quantities. This is a simple box and whisker plot, and I threw Charlene for a loop maybe because I changed the axis at last minute, but I thought it kind of showed the breadth of the change better than the vertical orientation. But they show the 3 comparison pairs to evaluate the general trends in the volume bends. So whether they're erosional or accretion, whether mean high water volumes are increasing or decreasing through time. And I also wanted to note, just for anybody's curiosity, we are using a defined mean high water instead of the actual mean high water, because the different data sets have different data coverage. When we use the normal mean high water of 0.34 meters, it resulted in data gaps in the shoreline. And so we're just using a consistent shoreline contour instead of the actual mean high water. And then next slide, please. So next steps, we are going to modify the volume bin geometry for full coverage and compare it to the existing bin volumes. I'm going to be working with Shane a lot to apply bias filtering techniques and then recalculate the volumes without that bias. And we started at Dauphin Island, but I guess I'm going to be moving westward until I get to Cat Island. And I'd like to pass it on to Sam Jackson from EL.
Thank you, Brooke. My name is Sam Jackson. I'm a research forester in the environmental lab. I'll be talking a few minutes about our dune vegetation products. We use the National Coastal Mapping Program hyperspectral. Next slide, Charlene. We use the National Coastal Mapping Program's hyperspectral imagery and LiDAR data as the inputs to a geoprocessing toolbox that we call Dune Veg, and that automates the extraction of various coastal vegetation metrics. The output metrics include vegetation presence and absence, normalized difference vegetation index, vegetation density, leaf area index, and the canopy height model. And so far, we processed the 3 years of data sets to coincide with the other data sets from the other team members from the Mississippi Coastal Improvements Program site. This toolbox was designed for using in ArcGIS Pro in the Windows 10 environment. It was developed with the Python programming language and integrates ArcGIS geoprocessing tools with NV image analysis capabilities using the NVPy module and the spectral band algorithms to derive the dune vegetation metrics. Next slide. This diagram shows the automated tool workflow that extracts the dune vegetation metrics using batch processing in ArcGIS Pro. The two main inputs here are the NCMP hyperspectral imagery and the LiDAR data. Each input's workflow creates a list of tiles that uses the overlapping desired area of interest. The metrics for each file in the hyperspectral list are then generated, and then NDVI is reclassified into vegetation density estimates based on the NDVI threshold values and consolidated into vegetation presence polygons. Each file in the LiDAR point cloud on the right there is listed to create a digital elevation surface model and elevation models and canopy height models from that input. You can click on the right here. It shows some of the examples of NDVI and veg presence and leaf area index from the hyperspectral imagery, and then the canopy height model derivatives from the LiDAR data. And we've got two publications so far showing the toolbox use, sort of a guidelines on that. So special report, also a journal publication of remote sensing that kind of describes the analytical processes of deriving some of this from a multi-temporal trend analysis of the products. Next slide. This kind of is a collective milestones for all of our work for our entire work unit and products for the rest of this FY and next FY. For the volume partitioning and hotspot analysis, there'll be ERDIC tech notes to describe the DEM segmentation using regional data sets and workflows for creating space-time cubes, and we'll further investigate methods to address the bias. And for next FY, we will refine the volume partitioning using the enhanced land cover products, and we hope to develop a land cover toolbox similar to the Dune Veg toolbox for all the pilot sites, and then publish a tech note for segmented volumes that pertain to the sediment budget analysis. And then also a tech note for parameter evaluation for the hotspot analysis, and then a journal article involving the uncertainty estimates for volumes. Next slide. As Charlene mentioned earlier, we'd like to request your feedback using this link here, so you can share your knowledge related to your work involving volumes for navigation, coastal flood risk management, ecosystem restoration, and emergency response. We would greatly appreciate your time in providing that to us. And this is just a few lists of the examples that we've gotten from feedback from the community. So that concludes our presentation, and I think we'll open up to any questions y'all might have.